in real person. Okay, so we are recording, and I'll make sure to get Cameron recorded as here. Everybody having a good week, I hope. Pivotal vote coming up in a few days. Hope you're planning on, if you're eligible, to vote. Okay, the plan today is to talk about inverse functions, this time from the top of the chapter. Remember last time I kind of skipped down to the middle of the chapter. We're going to go from the top. Also going to look at worksheet 3.3, get that finished up. Quiz 7, reminder for quiz 7, it is for credit. Check the assignment schedule. I am giving you credit for those quizzes and for your worksheets. They do give you credit. They will give you credit. Some may need that extra credit, so I will allow you to turn in worksheets. And if you're seeing something that you turned in that I need to go back and check, feel free to send me an email. So here's our plan for today. I'm going to be scribbling on the chapter that we worked on last time. Last time I scribbled all over it as we read through this. I'm going to start again thinking about this very first concept at the beginning of the chapter. Let me jump up to the top there.
Did we need to show our face or whatever?
What's that?
I didn't know if we needed to show our face real quick, just like the attendance thing. I got on like 2 minutes late. I was trying to figure out how to join, but...
Oh, let me mark you here. No, don't worry about it. I'll mark you here real quick.
Thanks.
Danny. You had a question, Kevin?
When was quiz 7?
Quiz 7. Let's see. Quiz 7. I have that due next Monday. This coming Monday at midnight. So back to that notepad. Where'd my notepad go? There. So quiz 7 for credit due 11/1. Oh, so that is also quiz 7. Quiz 7 is also due by Monday, giving you time over the weekend to catch up on things. Okay. Oh, and I wanted to let you know I am using a nice stylus pad. If that helps you when you're taking notes online rather than trying to use the mouse, if you'd rather take notes on your computer, of course, you can also always write with your pencil on a hard copy. But if you'd rather mark up a PDF, what I am doing is I'm opening that. I've saved the worksheet, or in this case, particular web page. I've saved it to a PDF file by doing a print and print to PDF. And I created those files, and then I simply open them in Explorer. And Explorer lets me mark them up. And you can always take notes on this and then come back and look at your notes. So that's a handy way to take notes if you like the electronic version. So I'm going to be marking this up again, thinking through this whole idea of an inverse function. Think of an inverse function as some function f. Oops. Oh, I need to turn on add notes. Here we go. Some function f. And it takes some input. Now we like to put x there, but remember what goes into the parentheses means any number. A stands for any number or some input. It's the input into the function. Something comes in as input. So a lot of time algebra gets confusing. You know, I talked to my wife and she said, well, why are we using letters here and there? Remember, the letter just represents some number. So that can be x, y, some letter representing our input into our function. Okay, so we have this function f, and we take some number x, we feed it into f, And what does it do to it? It does something inside of there to my number. And it cranks out some other number, y. Remember, y just represents some output. Whatever it takes as input, it cranks on it, does something to it. I don't know what it does. That's the function gets decided, it could do multiple things. We decide what the function does to our input, gives us some output. Now, if I have another function, I'll call it g. If it takes stuff into it and does something to it, if every time I fed it the output of f, it gave me back the number that was given to me at the first, if that always gave me that original number that I fed to f, if g, no matter what I gave to f, it would give me back the original number that I gave to that first function, then I would know that g is the inverse function f. That whatever g does, it does the inverse of what f was doing. So I will get back, and remember, what I feed into my inverse function is any input, some number. If what I feed into that inverse function is doing just the inverse of what f was doing, then we call it f inverse of x. So if I feed x into f, and I get f of x out, if I feed that into g, or into the inverse function, f inverse of x, remember, whatever input it takes, if I get back the original x, that means I do have a working inverse function. So if I get x, feed it to here, I feed f of x into here, that's my f of x. If I get back the original input, I am doing the inverse function. And that's why we see the upside down symbol, meaning I feed a number into its output, I get back what this number was giving me. Different ways of thinking about this inverse function. We talked last time about what things happen in inverse in the real life. Well, some simple things is I heat something up and I get something hotter. I get a hot thing, hot food. Well, if I take and cool my food, then I get my cold food. Heating and cooling are generally inverse. I heat up a nickel, I cool down the nickel, get back the original nickel at a particular temperature. Now, sometimes this is not one-to-one. Sometimes when I heat up my nickel or a penny so hot that it melts, well, just cooling it off, I don't get back my original penny. So there is a limit to the domain of temperature that I can heat up something that it is still one-to-one. I don't get back my penny if I've heated it up so much that it melts. Another real life thing, say I'm painting something, I'm mixing colors. I turn something, or I add green to it. And I feed it yellow and I'll get a orange yellow. I feed it white and I get green out. Well, is there some function that takes out the green? It's a little harder to do. In computer colors, I can take out the green because computer colors are simply three mathematical numbers, R, G, B, on my screen. In computing, it's easy to take out the green component of a color. But in paint, can I take out the green? Well, it's kind of mixed together chemically. It's hard to take a color out once I've mixed it in. But if I wrapped it in green and I can unwrap it and get my original package out, that would be my inverse function. As Christmas is coming, you take a thing, you wrap it in a box. Unwrapping is your inverse function. So wrap up my present, I unwrap it, and get my original present out. The unwrapping is my inverse. Physically inverse because wrapping is not changing my object. It's inside of a box now. I hand that box with my object inside it and unwrap it. So as we think of inverse and original function, think of those kind of concepts. Mathematically, we're unwrapping what we were given, or we're reversing the process of what we've been given. That's all an inverse function is. And the time they come in handy is when we're doing typically physics, undoing things physically or figuring out where something is going. If physical laws are in place, we might be able to have an inverse function. Here, the example they gave us, and looking at temperature, I know that I can calculate Celsius if I have a given Fahrenheit because of the way people have defined what Fahrenheit is. It's just another number matching temperature. And there is a one-to-one correspondence between temperature. Fahrenheit is just a slightly different number. I subtract 32 from Fahrenheit, multiply by 5/9, and I get my centigrade. So if I have 24 degrees centigrade, if I know this is 24, I could solve for F. Well, I could do that every time. If I've given 26 for centigrade and I want to know what F is, I can go through here and reverse the equation for specific temperature 26, and I get this as my resulting temperature. Or I can put it in the general form that anytime I have a temperature C, all I have to do is feed C into my formula, solve for F, and now I have the inverse function going from centigrade to Fahrenheit, where this function here gives me Fahrenheit to centigrade. Mathematically, if I take in any input F and I do this to it, the inverse of that, I'll call that C inverse of some temperature F. Or maybe I'll call it T just to generalize it. Some temperature T. To get inverse, well, that would be T times 9/5 plus 32. That's my inverse function. I'm unwrapping or returning, finding a way to get back to what my input was. Now, there is always, in a function like this, there's always going to be some domain. This particular function is a linear function. Any number I put in here will give me a valid output. I'm not dividing by 0 anywhere. So the domain of this one is negative infinity to positive infinity. That's my domain. And the output also gives me negative infinity to plus infinity, because I'm doing a simple linear operation on the input that I'm calling F. So all we're thinking about here then is this function that we call F inverse of X. Now remember, X is just some number. What I take as input, I do the inverse of what F was doing. So the value coming into it, the key thing is what this function is doing to its input. Now remember, it's doing the inverse of what this function did. It is not doing the reciprocal. It is not, even though you see the -1 there, that does not mean reciprocal. reciprocal would be f of x to the negative 1 power. That would be the reciprocal f. F negative 1, f inverse of x, that's not the same thing. So fx negative 1 is a reciprocal. F inverse of x, don't be confused thinking that might be reciprocal. So they kind of explain that it's not the reciprocal. The mathematicians, I bet you they fought about this when they were talking about this concept of inverse. Some guy said, well, let's say f negative 1 f. And some guy's going to say, well, no, people are going to be confused. They're going to think that's f to the negative 1 power. They probably argued over that, and finally they said, no, we'll notate it in this way. This means f inverse. And I called it unwrapping. Here they call it an undo. Or I think it's better to call it the reverse operation. It does the inverse of what the other function was doing. So basically, inverse is the best word to use. Doing whatever the other function was doing. So let's stop right here and do a few examples of simple functions. If I take a function, f of x, and say, okay, I'm going to take whatever number you give me, I'm going to add 1 to it. Well, the inverse would be to whatever number you give me, I'm going to subtract 1 from it. That does the inverse of adding 1 to it. So f inverse of some input says, okay, subtract 1 from the number you give me, and I'll get back my original x if you added 1 to me. Some other thing, how about 1 over x? What's the inverse of that? Anybody know? If I take 1 over x,
would it be x?
the inverse of 1 over x is
Isn't
1
it
over
x?
x. I take it, I do the reciprocal again and get back my x. The way to prove that? Well, if I say f of x equals 1 over x, put that in the form y equals 1 over x. Solve for x. Can you see how I multiply by x and divide by y? I get x equals 1 over y. Interchange x and y. Y equals 1 over x. This is my inverse. F inverse of x when f was 1 over x. Another way to think of it is 1 over 1 over x gives me back x. So this is an interesting one where the f of x is the same as inverse. And you can kind of think of that mathematically. 1 over x is the inverse of x. So this is a function where it is an inverse of itself. I take x, divide 1 divided by x. I do that again, and I get x back. But this has one interesting property. Where am I not allowed to do the 1 over x? What value is not allowed down here?
0.
0, right. So even though, I ought to be able to feed it any number, getting it back, because I've said f is defined as 1 over x, I automatically say, uh-oh, my of 1 over x is everywhere except where x is equal to 0. So I cannot have x equal to 0, even though you'd think 1 over x gives me x back any time. Well, if I ever say, well, I'm calculating 1 over x first, and then getting the reciprocal, there is one place where I'm not allowed to calculate 1 over x, where x is equal to 0. Otherwise, that function looks like a very simple function. So I jumped to that middle part of how easy it is to calculate f inverse is you solve for x and then interchange x and y. Because remember, I can interchange x and y because remember, that just represents some number. And y just represents some number. And the letter I assigned to that some number doesn't matter. So I can say, okay, if I want to calculate the reciprocal of a number, well, y equals 1 over the input you're giving me. All right, so let's continue more and scribble over this, looking at an example. And now we start getting into this. If I take the composite, remember the composite is defined by this. A better way to think of it is, remember, f inverse of giving me the input, or the as input, the output of the original x, f of x. I better get x back if this is true, if this is indeed the inverse. This will always be true if f negative 1 is the actual inverse. This will always be true. And this is a way to check my solution if I try to figure out what inverse of f is. This will have to be true. But remember, it will always follow that the domain of f of x has to be followed. So if I'm feeding this, if f is 1 over x, this will always be true, but it always depends on what the domain definition is for f of x. So what this is saying here is taking the inverse of x is, and if this is my definition of f of x, well, if I put that as input into my inverse function, and I think this is maybe f inverse of x, well, this is a way to check. If I take 1/4 of whatever I give to this function inverse, 1/4 x, do I get back my x? Okay, let's see. I take 1/4 of whatever I feed it. Okay, there's a 1/4 of whatever I feed it. And yes, indeed, I do get back x. Therefore, I have checked, yes, this is f inverse of x. Let's try the other way. Is f of the inverse. That means take f of x, feed the inverse function of x into it. Well, f of x multiplies whatever it's given by 4. Okay, I feed it 1/4 x. There's 1/4 x, feeding that original, meaning I take what I feed to you and multiply by 4, calculate it out, and I do get x back. Yes. So I know that f inverse of f of x gives me x, and f of f inverse of x also gives me x. Either way, one might be more easy to calculate, more convenient. So I can check it either way. Feed f into inverse of f, or feed f inverse to f and see if I get x back. But remember, I still have to follow the rules. F of x is domain. Oh, yep, any number. I can take any number, multiply it by 4, and I get a valid number out. Dividing any number by 4 also gives me a valid number out. So there is no limit on my domain. If I ever feed it specific coordinates just for testing specific locations, if I'm doing f of inverse of x, I better get the exact same coordinate value out. -8 better give me a -2. Feeding it a 0, I should get a 0 out if I'm testing any point of f inverse. Remember, f inverse means whatever I did to it, I'm undoing it. That means if I get an output, I get the exact same input that I gave it. In order for this always to work, that means my function must be 1, 2, 1. Let's think about what that 1-to-1 means. What 1-to-1 means. If I feed it some input and I get some output, that means if I get this output, I know I get back to the original input. Got me back to there. The only way this is possible is that for every one input, I get one output. If there were two outputs from two different inputs, I would know which one to choose when I went the reverse direction. If I ever got two, it's like, okay, I fed you a 1 and I got 2, and I fed you a -1 and I got 2. Well, when I get 2, how do I know which one I go back to, the -1 or the +1? And with that, if it was not 1-to-1, then I could not find my inverse. It must be one output. One input must give me one output, or I don't know which one to come back to. I'll get two possible answers. I can never have two possible answers because then I won't have a function. Remember, a function is defined that when I have one input, I get a known output. If I have a function that I don't know which output I'm going to get, such as square root of 4, what's my possible answer for square root of 4? Well, I know I can get 2, but what else will also give me 4 if I square it? -2 is a possible answer. What we define as, when I say square root of 4, what I mean is the positive square root of 4, because if I have two possible outputs, then it's not a 1-to-1 function. So typically we define square root as the positive square root of number for only positive numbers, because once I start taking the square roots of negative numbers, I go into the world of imaginary I, and that's not a real number. So we'll say in the domain of real numbers, we can only do positive square roots. And we define the square root of a number as its positive square root. So we will take things like parabolas, and we have to turn them into a 1-to-1 function. For example, x squared over all real numbers is not 1-to-1. I get a result when x is negative and when x is positive. The same y for different x's. This is not 1-to-1. Unless I say only for x between 0 and positive infinity. Then it's 1-to-1 by saying, sorry, I'm not going to consider numbers that are negative. Now I have a 1-to-1 function that I can do my inverse on. And I'll get a function that looks like this, which is square root. So I like writing it better this way when I'm thinking about where'd my pointer go. Oh, I like writing it better this way. That dot notation just is asking for confusion. So I would recommend thinking about it this way. I'm feeding f of x into its inverse, and I undo what f of x did to get back my x. But remember, it's the x's that are in the domain of f. Sometimes you don't even have to worry about that. Other problems, especially when you're dividing by something that has an x in it, you have to think, uh-oh, whatever's in the denominator better not be 0, or I'm dividing by 0 somewhere. Otherwise, for all the other x in the domain of f inverse, I get back my x. F inverse. And again, they remind us that it's not the reciprocal. This is f of x to the -1 power. This is f inverse. And I don't think we throw too many trick questions at you to fool you. This is f reciprocal. Now they actually go to a simpler concept as we think through this. When I have pairs of numbers, if I have f of x, and I have some pairs, like when I get a 2, I get, instead of putting a y here, I'm going to put f of x here. 2, when I feed it a 2, I get a 4. When I feed it a 5, I get 12. I know that f inverse of whatever its input is, if the input happens to be 12, I know f inverse of 12 is going to give me back 5, because f inverse takes this as its input. If it's given this as its input, it better give me this as its output, because otherwise it would not be the inverse. So f inverse of 12, I know will give me 5. F inverse of 4 will give me back 2. Do I know anything else about f inverse if all I'm given is this? Nope. I could try to guess other values, but if I'm given a pair, input-output pair, all I know is this f inverse will take me back to 2. Undoes whatever f does. I know that f inverse takes me back to 5. Otherwise, I don't know what f does. If someone said, oh, and f, by the way, is linear, then I might have a clue. I could draw a line between those 2 points and see that it's a line. But if all I know is I have these 2 pairs, the only thing I can say is f inverse will give me that as its output. Now I better have pairs that are 1-to-1. If I have something like this in my x and f of x, I have to check. Uh-oh, I just broke it. I get 2 different outputs for different inputs. Therefore, it's not 1-to-1. So therefore, there is no inverse of x, because when I don't have 1-to-1, I don't have an inverse. I could still say there is some function that does something for me, just like I have a parabola. For different values of x, I get the same y. That's perfectly valid function, but its inverse is not a function. Its inverse would look something like that, and that is not a function. Give me one input, and I get 2 different outputs. I could define that mathematically as I get the plus and minus of some value, but that's not the valid definition of a function. It needs to be a 1-to-1 giving me an input, I get 1 output. So whenever you're looking at pairs, all you're looking for to verify that it's an inverse is that, yes, there is a unique output for every input. Otherwise, it's not one-to-one, and then there is no inverse. It is because inverse require a one-to-one function. Everything has to be one-to-one if I'm going to find an inverse. And there are some exercises that simply test that. And all we do for the inverse is reverse the input and output. If I have a table, it better be the inverse of the table. If I get 12, I get back 5. So feed the input into that function, I get back my original input. Feed this into this function, I get a 4. Feed that 4 into this function, I get back my original. Then it is my inverse function. Simple example, if when I feed this a 6, I get back 2, I know that in order to get 6, I must feed my inverse function a 2. Now, a way to test whether they're inverses of each other, this is where we go back to that original rule way up here that they are inverses if I feed one to the other and I get back my x. And I could decide which one might be easier to do. Either one should give me back my x. And what I like to do is I like to do it both ways to just give me mathematical practice. So let's go down here and confirm whether these two functions are inverses. Let's do it both possibilities here. So f of x is 1 over x plus 2. G of x is 1 over x minus 2. Well, let's put that in parentheses. Let's feed that into this x and see what I get. So 1 over x minus 2 plus 2 gives me, well, the 2's cancel out. I get 1 over x gives me x. So yes, they are inverses, but pay attention to the domain here. The domain of this one is x can never be negative 2. So let's add that to here. X is never equal to negative 2. Even though 1 over x should always be good, well, except for where x is 0, well, that will be 0 when x is negative 2. So x can't be negative 2. But I do see that for all other x's, I do get x back. So yes, they are. Let's do the other way. Let's do 1 over x minus 2 and feed into that x the 1 over x plus 2 for x. That becomes that. So I get 1 over x plus 2 minus 2. Better put that minus 2 in the right place. I was almost putting the minus 2 there. That would have messed me up. Remember, I'm doing 1 over x and then subtracting 2 from the whole thing over here. Well, 1 over x plus 2 is equal to x plus 2. And then I subtract 2 from that, and I get back x. Uh-oh, but the domain is x cannot be equal to negative 2, or this would blow up. So I have the same domain, but I do get x back for all other values of x. So yes, either way, I tested, what did I test here? This was g of x what I tested here was f of g of x. I took g, 1 over x minus 2, and fed it to f. Here I took f and I fed it into g's input, and I get back x. Proving, yes, indeed, f of g of x comes out to be x, so they are inverses. G of f of x gives me x. Another way to prove that, yes, they are inverses. So if I get back x from that one, this also gives me x. I have checked it twice that they are inverses. Usually one is sufficient, but it's good practice to try both just to test your checking skills. Now let's do some checking on our own and just see if they're inverses. And we can even make up some as we get better at this. So x cubed minus 4. Here I take the cube root of x plus 4. Now, even before doing my math, let's think about this. If I take this guy's input and add 4 to it, well, if I'm feeding it x cubed minus 4, I'll get, and then I add 4 to it, I will get x cubed back under this radical. Well, the cube root of x cubed gives me back x. So that sure seems to make sense. If I go the other direction, I take the cube root after, let's see, no, I cube something and then I subtract 4 from it. Well, let's see here. Cubing this will give me x plus 4. Subtracting 4 from it, they'll get back x. So it sure looks right. Let's go ahead and write it out. So x cubed minus 4, feeding this to it. So cube root of x plus 4 taking that and cubing it and then subtracting 4 from it. Well, taking that and cubing it gives me x plus 4, and I subtract 4, gives me x. Now let's do the same thing going the other with the that was, what was it? That was f of g. Let's do g of f. Well, here's what I do in g. So cube root of, this time I have to feed it my f here where the x is, x cubed minus 4 plus 4 then. Now that gives me cube root of x cubed, gives me back x. Yes, both solutions, or both g of f and f of g, give me back x. So yes, they are inverses. And check the domains here. Cube root, nice thing about odd roots, there's only one solution. So it is 1 to 1. So it's valid over all real numbers. There is nothing dividing by 0 to give me any problems in my domain. How about this one? I take 1/3 of any number. Well, the inverse of taking 1/3 of a number should be multiplying that number by 3. So I'm pretty sure this is not the inverse. Let's prove it. Let's take f of g. And remember, many of these problems will require you to show your work. F of g is, I take g and I cube it, because f cubes whatever it's given. So g is 1/3 x. Cube that, what do I get? Well, 1/3 cubed is 1/27, and x cubed is x cubed. So I get 1/27 x cubed. Definitely not x. So definitely not if I test it this way. Let's test it the other way. G of f of x, well, what does G do? G takes 1/3 of its input, and its input is x cubed.
Is that a 27 underneath the?
Here?
Yeah.
Yep, yep, that's 27, yeah.
You got that just from cubing the 3.
Yep. Yeah, 3 cubed, 1/3 cubed gives me 127. 3 times 3 times 3. And now g of f of x gives me 1/3 of feeding f of x into that. Well, I get x cubed over 3. I can't simplify it any further. That's definitely not equal to x. So therefore, no, they are not inverses. Well, it's simple enough. What is the inverse of cubing? Well, it'd be the cube root. That would be the inverse, the proper inverse. Proper inverse of taking 1/3 of something would be multiplying it by 3, gets me my x back. So some are simple enough. I would say it's pretty obvious just looking at this that I know taking 1/3 is not the same as doing the cube root. There may be a number that does give you x back for a specific x, like I feed 0 to this, I get 0 out. Oh, I feed 0 to this, I get 0 out. That doesn't mean they're inverses. That just means for one special value of x, I do get the same value. The two functions cross at x equals 0. Otherwise, this is a linear function, gives me a slope of 1/3. This is a cubic, giving me something like this. And they cross at x equals 0.
So if only works, that would be a no.
Yep, yep. These are, I'm checking it both ways. Yeah.
Both of them have to work.
Either way, and sometimes one way is a lot easier. Here I had to cube 1/3 and get 1/27. Here all I did was divide by 3. So this was a easier one to check. And sometimes you don't know how easy it's going to be until you start feeding one into the other and say, wait a minute, this is getting really hard. Let's do the other one. Oh, that was a lot easier to show whether or not I got x. So I don't think in our quizzes we give you really tough ones, but that's what the mathematicians do. As they get harder and harder functions, and they want to say, hey, are they inverses? One may be much easier to calculate than the other, to prove whether one's an inverse or not an inverse. And that's the trick to the mathematical, as you get more complex problems, you have different ways of solving the problem, and you start working on one, and you realize it's getting really hard, so you go another way. And as you practice this kind of thing, you start recognizing patterns, and some guy will come up with, hey, this simple way of solving this really hard problem is this other path I took. And some really hard problems, they find a simple path to solving the problems, and they win Nobel Prizes because they found a simpler path to whatever other mathematicians all through history were trying the hard path. And that's how many mathematicians became famous. They found the easy path to solving a problem and made a really hard problem simple and obvious, and they then could retire early. Now let's see for this one. Does it make sense? Let's just look at, without even solving it mathematically yet, I subtract 1 from a number and cube it. If I'm given this number, well, subtracting 1 from that gives me the cube root of x. And if I put cube root of x in here then and cube it, I should get back x. So it sure looks like they are reciprocals. Let's prove it mathematically just to practice our skills. F of g of x is, well, take g of x, cube x plus 1, and put it right here, and then x minus 1. So I'll take that. Whatever goes in there, I'm going to take subtract 1 from it and cube it. Well, cube of x plus 1 goes there. All right. Oh, don't forget the 3 there. All right. Subtract 1, I get cube of x cubed gives me back x. Done. If I want to do the other way, g of f of x, well, g is cube root of something plus 1. Well, the something is this x minus 1 cubed cube root of x minus 1 cubed gives me x minus 1 plus 1 gives me back x. I'd say the difficulty is about the same for those. Handwriting was a lot worse on that one though. And remember, the domain becomes the range of the other one. If we have dividing by zeros, we have to worry about that. In this case, is there a problem anywhere for any value of x? No, any number anywhere cubed doesn't give me a problem. And same thing here, cube of any number doesn't give me any problems. Therefore, the domain is all real numbers. All real numbers are and the range is all real numbers. This takes all real numbers and generates any other real number. So the domain of f is all reals. Its range is all reals. That gets fed into G. All reals into G. Give me all reals out. So domain and inverse. I only need to worry about this typically when I have anything divide by 0. When I'm doing becoming a square root. Remember, if I put a negative number in a square root, I get imaginary numbers, a whole different world of numbers that we're saying we're not going into. We're doing real number algebra. So this is that in diagram form. The numbers that can be fed into x and into f, remember that's the input into f, have some range of f. That's my output of f. For the inverse function, the output of f becomes my input of the inverse of f inverse. Input of f inverse better get me back the same range because that's going to now become my input of f. So the output of f inverse gives me the input of original f, and then I have in f and the inverse. And remember, this all depends on that one-to-oneness. That's why we have that part of this chapter has that, is the function one-to-one? If it's not one-to-one, don't even think about this. I'll have a way, I guess a way to think about it was f gives me two different circles, and so going the other direction, I don't have one function to work back the other direction, therefore can't even think about it. One-to-one has to be true before I can even worry about range and domain. And that's why we'll have some simple checks. Is a function one-to-one? Does its mirror give me a function back? If I do the mirror image, or if I do the horizontal line check, or the vertical line check, that's the one-to-oneness going both directions. And that's why one-to-one becomes so important, because I have to have an input. If I have two corresponding inputs give me the same output, then I've got a problem. One-to-oneness fails, and then I don't have a function. If I don't have one-to-oneness, I don't have a function. So therefore, they're explaining the quadratic function isn't one-to-oneness, except if I decide to limit to a certain domain. Then I do have one-to-oneness in this range. Whatever's in here is 0 or greater, then I'm good, and I'm looking at the function, in this case, starting at 1 and forward, that is 1 to 1. Once I start looking at anything on this side of x, I'm getting this, and no, that if I go there, I'm not 1 to 1, so I say, no, I'm not going there. I'm only allowing this for my x's as the input to f of x. And thus we define our range. And this, for x 0 or greater, I'm taking the positive root, 0 or greater, I can go then into the range. That becomes the range of f, gives me the valid domain of the original f. The domain of f of 1 is the range of f. So 1 to infinity is the range that this will have, or is the range this will have. That becomes the domain into the inverse function. The output of f is the input of inverse f. And mathematically, they're interesting because they allow us to solve harder problems. So that's why they threw this into college algebra here, because it's an important concept in further math. And for you to understand it will help you get that idea into your math toolkit, and maybe knowing this, understanding inverses will help you sometime in your future. At least it's giving you a little mind exercise, understanding and working through a little tougher problem. And again, we got this one-to-oneness requirement. So if I have a function 1 to 1, the range of the original is the domain of the inverse. Let's take a look at looking at the range and inverse. And they give us a particular toolkit of functions. Which of these are not 1 to 1? And is there a restricted domain that will make them 1 to 1 across that restricted domain? Let's take a look. Is f of x equals c? Is that 1 to 1? What do you think? I have a constant c. Remember, that gives me a horizontal line. Is it a function? It is a function. But is it 1 to 1? Do I have a different output for every x? Well, I can't do the inverse of f. It does take any domain as its input, but I get the same number all the time for its output. So given an input, c, it fails the horizontal line test. I don't know which x gave me that c. So I don't have one-to-oneness on this function. Although it is a function, it's not 1 to 1. So that one I can't do the inverse. This one, for every value of x, I get x back. Well, that's essentially a diagonal line. And yes, I do, for different x, I get the new value of x. Yes, this is 1 to 1. Quadratic, is it 1 to 1? Looks like this. Uh-oh, fails a horizontal line test. I can get the same value for a negative x. Negative 1 squared gives me 1. 1 squared gives me 1. So it's not 1 to 1 unless I decide we're only going to define that for positive x. So possible domains are 0 to positive infinity. There it is 1 to 1, because I get this. It's also possible to be 1 to 1 if I define the domain of negative infinity to 0. I could say, okay, it's 1 to 1 if I don't consider those. So I have the choice of which domains to use to make this 1 to 1. So the restricted domain of this or this restricted domain will make that 1 to 1. If I use this one, I might get crazy things happening on the square root side, but at least I do have 1 to 1-ness, and I have the coming down to 0 or leaving 0 and getting larger. But both of them, then it wouldn't be 1 to 1. So restricted domain of either of those will make it 1 to 1. Cubic, graph that. It's going to look something like this. And if there's a cube somewhere in there, it may shift left and right or up and down. This simple cubic, yes, it is 1 to 1. I'm good. And there are no values where it blows up. Uh-oh, this guy is 1 to 1. Looks like this. Gets really, really big when I'm positive. Gets small as I go larger. It's really, really big negative. And then gets small as I go larger negative. It is not defined at x is 0. So the domain is x not equal to 0. Or if I want to define it in the parenthesis format, I could say negative infinity not 0 union with not 0. Oh, I used the wrong nomenclature. That is a curved parenthesis. Sorry. Not 0. This is the other format of not being able to 0. Negative infinity 2, but not including 0, combined with not including 0 all the way up. It's a crazy function. Sign changes when I cross 0, but it will be 1 to 1. Because nothing here ever hits that one. Vertical line test and horizontal line test work. Reciprocal squared, is that 1 to 1? Well, let's see, graphing it, when I square a number, it's going to get really big as I go this direction, so 1 over that's going to be really small. Oh, I can't have 0. And on the positive side, it's going to be really big as I'm close to 0 and get really small as I go positive. Oh, it fails the horizontal line test. It is not 1 to 1. I could make it 1 to 1, very similar to the quadratic, by restricting the range to negative infinity and not 0, or not 0 all the way out to positive infinity. It's 1 to 1 if I just go here. It's 1 to 1 here, but not both, and never 0. So the restricted domain would be this or this. Restricted domain. Cube root. I can take the cube root of anything and get a single number back. So this is 1 to 1. Square root. Uh-oh. I have to define my square root as I'm taking the positive square root, and x can never be less than 0. Absolute value of x, well, I can take the absolute value of any x. The problem is negative numbers become a positive numbers stay positive, fails a horizontal line test, so I have to restrict either to 1 or the other, all negative to 0, and I can include 0, or 0 all the way up to positive infinity to make it 1 to 1. If I want 1 to 1, I have to restrict it to one of those domains. And depending on the problem I'm working on, I could decide, just like this here, I could decide which restricted the domain am I going to choose to make it 1 to 1. All right, let's help you a little bit with the finishing up that worksheet. We got it almost done last time. Let's get that finished. We went over the horizontal line test, checking one-to-oneness.
Do you have any paper back?
Oh, yes.
This is 3.3.
Yeah.
So we worked on this Tuesday.
I started today, and if you want to finish it up, uh-oh, I throw it away. I don't remember. I think. Yeah, if you want to do it on your laptop, I'll let you finish that. I'll help you do that. If you want to just take notes, and then you can print it out. We got almost to the last one. Basically, here's what I'll do. Since I'm recording this, I'll skim through this, and you can check the answers as we recorded it.
Okay.
And also the recording from Tuesday is available. And here's the last one. This is actually the last problem on that worksheet 3. Basically, we want to find the inverse of this function. And remember how we find the inverse. F of x is 16 plus cube root of x. Remember how I can write that out? I can just say y equals 16 plus the cube root of its input. Think of that x as the input to f of x. I could right now exchange x and y and then solve for y, but let's solve for x first, and then we'll do the final interchange. Okay, so let's get what basically we want to get x by itself, so we subtract 16. Y minus 16 equals cube root of x. Well, to get x by itself out of the radical, I cube everything. So y minus 16 cubed equals x. Okay, so this means to get x back, I take my number and I subtract 16 from it and cube it. Well, to now define this as f inverse of some input that I decide to call x, just basically means in reverse x and y, say this is my input to my function. Take whatever input you give me, subtract 16 and cube it. I know I will get x back if this is what you gave me at the start. So there is my f inverse. Simply solving for x and then saying, okay, if you give me this as input, I know I'll get x back. So put x in there, x minus 16 cubed. I now have f inverse. And I think I'll stop there, give you a little extra time. If you have any questions, want to go back over anything? Otherwise,
I just have a question. Dan, on the worksheet on the quadratic practice, it still shows that grade is like not being there. Like, I turned that in, so I was just wondering if you were be able to fix that or whatnot. My coach was wondering about that for baseball.
yeah, just which number was that?
It was the worksheet on quadratic practice from October 1st.
Yeah, I think I got your
it-
email. I hadn't gotten back to that. I think somebody called me right when I was looking at that. But if you don't see that, I'll, and just, don't be afraid to send me another email, just say another reminder. Don't
Yeah,
worry about
sure.
sending reminders. 'Cause
Yeah,
it's easy.
no worries. It said an F in there, like 0 and incompleted, but I know I had done that. So
Okay.
if you need a picture or anything, just let me know. I can send that
All right.
to you.
And
Thank
anybody, if you want to do worksheets that you haven't done, upload the picture to Moodle and then let me know that you got it in and I can go back and check that in. Remember, those worksheets are for credit. And feel free, if you're stuck on any problems, send me an email. I'll be happy to give you a little help. And these videos are available in the calendar. I will stop the recording.
Is the quiz 7 that's due on Sunday
Monday.
or Monday?